Okay, so continuing in 7.3, sample means, we are going to talk about some CLT magic. Okay, in CLT magic, what CLT stands for is your central limit theorem. We're going to talk about it here, but I want to do this first. I want to show this to you, and you're going to see it. You're looking at it, it's like, that's like magic. Yeah. Oh, yeah. Yeah. Okay, so we're going to look at a sampling distribution, okay, of, and write this down, okay, heights of humans at a daycare, okay? So the height of humans at a daycare. And we're going to look at a little scale here. This will be our graph that we look at. What are you going to have at a daycare? You're going to have some people that are like 2 feet tall, and then you've got some people that are 3 feet tall, and then 4 feet tall. And then over here, you've got some adults too, because it says humans, it's not just the kids. Okay, it's not just the kids. So what would you expect here? What would you expect? If I were going to do a quick graph of this, we would expect, at least I would expect, that you're going to have some down here, and then you're going to have some over here, right? And this part of my population is probably going to be bigger than this, okay? Because at a daycare, you've probably got a few adults, okay, or a handful of adults. Hopefully you got a few adults. You got one person. You put a lot of trust in that person, all right, to handle all those little animals. So it probably makes sense that if I were looking at it, it'd probably be bimodal, right? A bimodal population, okay? Bimodal population, which means we're gonna have a lot of these. So we're gonna have a lot of these, and then it's gonna probably go down unless you have some really unusually tall kids. And then there'll probably be another mound somewhere over here, okay? So you have a bimodal population. Why is this one bigger? Okay, because this is all the kids, and this is the adults, and at a daycare you would expect to have more kids than adults. Okay, so the sampling distribution, okay, they're bimodal. If this is a picture of my sampling distribution, it's bimodal. Okay, and we're going to calculate X bar for all of these, okay? So let's think then, okay? Let's think. So we've got our bunches of students down here, okay? We're going to look at a bunch of different graphs to try to prove my point here, okay? So we're going to look at here, we've got all these kids, okay? And then over here, we've got a couple adults. And if we were to sample here, okay, and find the mean, find the X bar, find the average height of humans at a daycare, I would say that would probably be down here, somewhere over here. That's where your X bar would be, right? Because we've got a lot more kids than we have adults, so this is going to get pulled in that direction, okay? So then you have another daycare, okay? You have another daycare like this, okay, and again, your X bar is probably going to be down here somewhere. Okay, and then you have a daycare where there's just not that many of them. Maybe it's a smaller daycare. So if we're talking about the average, okay, we're talking about the average, that average might not go as far over. Okay, we had a lot of these. Maybe this one's not over as much. Maybe that's where my X bar is. Okay? So in any event, we're getting all of these X bars from all these daycares. You go to the daycares. Okay, you go to all the daycares and you find the average height. You line everybody up, you measure them, and you take their height. Okay, and these are all represented as their average height. That's the mean height at that particular daycare. Well, what happens in the sampling distribution is you look at a bunch of samples. You look at samples and samples and samples and samples and samples, and then we're going to try to find something about all of those samples. So when we do that, okay, we want to create what's called a sampling distribution. Well, the magic that happens, let's think about where all those X bars are going to be. I have these populations. We've talked about it, okay? You've got a small one here, you have a bigger one over here. There's more here than there is there. But what happens to all those X bars? Where are those X bars going to pile up? In the middle. The X bars pile up in the middle. That's even if we have a bimodal population, okay? If I had a regular population, okay, if I had a normal population, and I took all these averages, right? I took all the averages, we would expect them all to happen in the middle. We would expect them all to be there. We took this, the mean of this population, another one that's normally distributed, we expect those to come right in the middle. But for something like this, even if it's a bimodal population, if you find the X bar for all of these, your sampling distribution is going to become normalish. Your sampling distribution is going to become normalish. Okay? Normalish. Your mean is going to be the same as the mean of the population. Okay? The mean of the population. And our standard deviation is going to be equal to the standard deviation divided by the square root of n. Okay? But the beauty of it, the beauty is, even if you're talking about a bimodal population, when you find those averages, and you take a sampling distribution, which is a collection of all of those little averages, that you get something that is normalish. Okay, and we can use the normal model to describe the situation. Okay, so let's just say that this mean of x is 48, and let's say that, I probably should have mentioned this earlier, I didn't, okay? Back at the beginning, go add this to your notes. The mean of the population of daycares is 48, and the standard deviation is 16, okay? And our sample size was 60, not 60. Our sample size was 64, okay? This went with our first one, okay? 48, so that's like what? 4 feet, okay? 4 feet. So let's say for our sampling distribution, okay, we got a mean of 48, and for our standard deviation, okay, for our standard deviation, we take the sample standard, the population standard deviation, which is 16, and we divide by the square root of our sample size, which is the square root of 64. So I get 16 divided by the square root of 64 is 8. So it looks like my standard deviation is 2. So if I wanted to create this is 48, and then we go 2 this way and 2 this way, so that's going to be 50 and 46. And then we go 2 more, 52 and 44, and we think back to this, the empirical rule, mean 68, 95, 99.7. Whew. That's what we do, right? So my mean's at 48, right? 68% of the values. 68% of the values are going to be between 46 and 50. 95% of the values are between 44 and 52. Okay? So this stuff isn't going away. It's not going away. This is even if we have a bimodal population. Okay? So here are your key terms from this. I don't know if it's in these notes or not. It's not. So I'm going to give it to you. Okay? Here we go. These are what we leave with. Okay? we had our, you remember what the picture is, I can almost see it. I'm gonna put the picture back up. Okay, you had this, and then you had this, right? So it was a bimodal population, okay? A bimodal population, okay? And the distribution of samples is bimodal. Now, you gotta know, the distribution of samples is not equal to a sampling distribution. Okay? Distribution of samples is just where your samples are. Okay? We're talking about a sampling distribution. So the distribution of samples is bimodal. These are where your samples are. You've got some here, you've got some here. But when you look at a sampling distribution, that means you're finding the average of this. The average of this sampling distribution. And you find the average of another sampling distribution, or the mean. You find the mean of another sampling distribution. Okay? And the sampling distribution is normalish. Normalish, okay? Where we have normal, the mean, and the standard deviation, okay? And that's what the central limit theorem does for us. It is magic, okay? You may not want to embrace it, but it is magic. It's a bimodal population. No one would tell me that these two things are the same, okay? You've got some here, you've got a few adults, and then you've got a ton of kids in this daycare, okay? So here are the points that we walk away with, okay? If the population is normally distributed, right, or normal, so is the sampling distribution. So that's what I talked about at the beginning, okay? Or maybe in the middle. Maybe it was in the middle to get this out of the way, okay? So that was when I said if we had this one, and then you had another one that was normally distributed, and you had another one that was normally distributed, and we find the means of all of these, it's easy to see that the mean of the sampling distribution is also going to be normal, okay? So if the population is normal, so is the sampling distribution, okay? Now this is where it gets a little, this is now the CLT comes in. If the population
At this time, could we have all walkers,
is
drivers,
not
and grade 8 or just
normal, the CLT tells us the sampling distribution of X bar will be normal. They throw this disclaimer in most cases. We're just going to say it's normal as long as your sample size is greater than or equal to 30. Okay? That is what we're talking about with these things. Okay? That is the punchline. Okay? So we're going to look at the notes quickly. Okay? And then I'm going to end this because I got to have lunch. I'm running around to my lunch here, so we'll probably shut this video down. But I want you to understand this. It's so important. It's central to the course. That's why they call it the central limit theorem. We're going to talk about a lot of theorems. It's probably the only theorem we talk about. Let me see how much time we get here. This video. Now, I got a couple minutes. Let me see if I can get through the rest of this. And if not, that doesn't make sense. You tell me
now
what.
got grade 7, room
So-
248 to
Here's our central limit theorem right here. Okay. Oh, you can't see that. They talk about this another strange population. Here's another strange population. But you know what's going to happen here? You know what's going to happen? You can't erase your board, that's what's going to happen. Okay, so even this population, look at this population. Okay, a strange shape, isn't it? Far away from the mean, but guess what happens? If I start taking means of populations like this, those means are still going to be in the middle, which makes our sampling distribution normalish. Okay? So the last thing I'm going to ask you to do for this video, that will almost get us through 7.3, but not quite, because I have to cover what's in, oh, this is weird. This page was supposed to be next in your notes, so it's probably messed up in the order that I gave it to you, but you guys can flip that over before you put it in, okay? This is the next page. So what do you think the X bar is going to look like of samples of size 2? Here's my samples of size 2. Here's my distribution of means. And then here's my samples of size 5. And then here's my sample. Look at the beauty of that. As n gets bigger, what happens to the distribution? The sampling distribution becomes normalish. You could make a case, you know, someone could say, oh, that's kind of normalish. But then you go here and you go, oh, well, we're really getting more normal. N is 25. What do you think would happen if I made N 30 or 35 or 40? Well, your sample size goes up, your variability goes down. We would get a graph that's even closer together, okay? As your sampling size goes up, your variability goes down, okay? In this first one, let's go back to the first one, right? In this one, let's think about what our standard deviation would be. Probably pretty large, right? Average distance from the mean. And then we go here, well, average distance from the mean is going down. What happens here? We get a lot more values close to the true mean. What happens here? They're all piled up by the true mean. Okay? That is our central limit theorem at work. The normal condition for sample means, here it is. In most cases, if n is greater than or equal to 30. That takes care of what we're doing in 7.3. There's part of chapter 10 we're going to do with this, and that'll be at the very end. That'll be your next video.